Alright, hello everyone. Sorry it's been so long. These videos take a while to make, a lot longer than you think actually. But today we're going to talk about atomic packing factor. From now on I'll call it APF. And this is a material science, crystallography, metallurgy, etc. concept. And it's a measurement of what fraction the volume of a repeating cell is occupied by the atoms. In metals, as I'm sure you know from chemistry, the atoms will stack on each other and then create an electron cloud where they're all shared. So the way the atoms stack is going to be different, and we're going to talk about four of those today. We're going to talk about simple cubic. We'll talk about face-centered cubic. And we'll talk about body-centered cubic. And we'll talk about hexagonal close packed. So we got SC, FCC, BCC, and HCP. And we're essentially going to derive just what that fraction is, the fraction of atoms in a certain volume. So one assumption we make while we're doing this is that all of these atoms are going to be hard spheres, which is something I'm sure we're comfortable doing by now. So first we'll start with simple cubic. And we know that APF is going to equal volume of the atoms divided by volume of the cell. And if we have a simple cubic cell, we're going to have our cube and we're going to have our atoms, occupying the corners of these. Now I'm not drawing this to scale because in a real simple cubic, if we were to hold it up close like this, it would look like this. So the atoms are touching. Now what we're going to do is it's going to involve some it's going to involve some 3D visualization, and I'm not sure how best to show that with drawings instead of little figurines, but we'll see how well we can do. So each one of these is an atom. Well, we'll look at that in a second. So we're going to take our atom and we'll 3D it. So that's the sphere, right? And since we're cutting off on the top, that means we're down to half a sphere, right? And then we're cutting through an atom on the side, so that means we're down to a quarter of a sphere. We'll get rid of this section. And then we're going to cut through the atom on this plane as well. So half, half, half. And each one of these corners is going to have 1/8 of an atom within the cell. Remember, they are stacking, and what we're looking for is a repeatable unit. So these extend back in 3D as well. We're going to have up top so I'm trying to draw this as 3D as possible, but again, not an artist, that's why I became an engineer. Right, so the most repeating unit is going to be this cube right here. I know I'm not a great drawer, but we draw our cube, and so we have 1/8 of an atom here. Just about here. Then we're going to have 1/8 of an atom here, And remember, it's going up on this plane too. 1/8 of an atom here. Oh, that's what this whole thing is. 1/8 of an atom here. Right, hopefully you can visually see that. So, with that in mind, we need to find our V atom, right? And if we just went through how there's 1/8 in each corner, and there are 8 corners. So that means it's going to be equal to 8 1/8 atoms times the volume of a sphere. Right, so volume occupied by the atoms is going to be equal to the volume of the single sphere, 4/3 pi r cubed. Alright, so now we need to find the volume of the cell, right? And it's a cube, so we're going to have some length a, right? And volume of the cell is going to equal a cubed. In this case, what is volume of the cell? Well, if these atoms are touching each other, A is going to be 2r, right? R being the radius of the atom, R equal radius of atom. So V cell equals 2r cubed. V cell equals 8r cubed. So APF can equal 4/3 pi r cubed divided by 8r cubed. R's cancel out, and we're left with 4 pi over 24, which is going to equal 0.52. And that's the atomic packing factor of simple cubic. So in this simple cubic arrangement, this means that 52% of the volume of the cell is occupied by atoms. Alright, so now let's move on to body-centered. Oh, no, let's do face first. Face-centered cubic. So in this orientation, I'm not going to draw it 3D. We're going to have a half atom in each face. Right, so when we cut it in half, we're going to see, just making sure it all touches where it's supposed to touch. So we have our 8th atoms up here, and then we're going to have 1/2 atom right here in the face. Right, because it's going to be a full atom until we slice it down that repeating unit, if you can see that. So the issue is we are not touching here anymore. So that means V cell is going to be a little more complicated. But first let's find our V atom. Alright, so first we know that there are going to be 8 1/8 atoms on the corners, plus how many half atoms are we going to have? 1 in each face. There are 6 faces on a cube, so 6 half atoms, times the volume of a sphere, 4/3 pi r cubed. So that means we're going to get 1 plus 3 for 16/3 pi r cubed. And that's the volume of the atom. Now, we need volume of the cell. So we remember from earlier, we have our A term, and V cell equals A cubed. Good with that? So now what are we going to do? Well, these aren't touching, but these are. Across this main diagonal, all of these atoms are touching each other. So we can take that triangle and do some trigonometry. So we have A by A, and then we're going to have this length, which is going to be 1 radius, and in here they're going to be 2 radiuses, because it's a diameter, 2r, for a total of 4r. Now, we need to put A in terms of r, because that's what we're looking for. So we know that from Pythagoras' theorem, a squared plus a squared equals 16r squared. 2a squared equals 16r squared. A squared equals 8r squared. A equals 2 root 2r. So we're going to take that, plug it in over here. We're going to get that the V of our cell is going to equal 8 times 2 times root 2 times r cubed for 16 root 2 r cubed. All right, so we good there? I'm going to assume we are. So now APF is going to equal 16 pi r cubed divided by 16 root 2 r cubed. Cancels out, cancels out, cancels out, cancels. Oh, there's a 3 down here. So that's going to equal pi over 3 root 2, which should equal 0.74. So 74% of the volume occupied by this cube is going to be, well, 74% of the volume in this cell is going to be occupied by atoms. What I'm doing right here is I'm pulling out a calculator to make sure that .74. All right, so we are good. Hopefully this is making sense to you because it's going to ramp up in difficulty. Now we're going to talk about body-centered cubic. Now in a body-centered cubic, we're going to have our cubic cell. Right, but instead of the atoms being on the faces, we're going to have a whole atom in the center. Of the cube. Might be better if I make it a different color. It doesn't matter. And then we're going to still have our 1/8 atoms in each of the corners. That one actually came out not half bad. Nah, I don't know how I did it. Anyways, this is also not drawn to scale, but that's the idea behind it. So, first up, as we've done before, we need volume of the atoms, and that's going to be equal to 1/8, or 8 1/8 atoms, because 8 corners, plus 1 full atom times the volume of a sphere to equal 2, so 8/3 pi r cubed. Now we need volume of the cell, and this is where things begin to get tricky, because we are no longer touching through the face. This one doesn't even really come out to the face. We're not touching on, so if I were to draw it like this, these aren't touching, right? And this atom is back in there. It's not in the face. However, the atoms do touch along the main diagonal of the cell, right? And just as before, we're going to give this A, and we're going to say that V cell equals A cubed. Right? They're touching along the main diagonal. So if we draw our cube, we're going to have the atoms touching from these main points down the main diagonal of the cube. So this is A, this is A, this is A. And in order to complete this triangle, we need that distance right across the bottom plane, right? So we have this triangle that we're going to work with in order to find that distance. So this is A, right? That's this right here. This is the diagonal, this is the main bottom diagonal, and we don't know how long that is. We're just going to call it X. And we know that this one we have 2 half atoms touching a whole atom for total diameter of 4r, just like with face-centered cubic. Or 2 radii touching a diameter for 4 radii. But what is X? Well, we also have this triangle. Right? From down here, we have A, and we called this X. So what is X? Well, X squared is going to equal 2A squared. X is going to equal root 2A. So we bring that back up in here. So now we have our triangle. A, root 2A, and 4r. I'm going to clear off this one right here. Alright, so now we got to do our trig again. We're going to get that 16r squared is going to equal a squared plus 2a squared. So 16r squared equals 3a squared, right? And we're going to get that 16 thirds r squared equals a squared. And then finally a equals 4 over the square root of 3r. And because v cell is a cubed, we're going to go ahead and cube that, and we're going to get 64 divided by 3 root 3 r cubed as our volume. So our APF is going to equal 8 thirds pi r cubed divided by 64 3 root 3 r cubed. R cubes cancel out. 3's cancel out. 64 turns into 8, and this 8 goes away. So now we're going to be left with 8 root 3. Hold up. No, not 8. You can get all the way through this and then mess up with algebra. Don't feel bad. So we're going to have pi root 3 over 8, which should equal 0.68, but again, I'm going to go check on my calculator to be safe. Make sure I'm not teaching you wrong. Pi times root 3 divided by 8 equals 0.68. And so that means in the body-centered cubic, the packing efficiency, or they can be interchanged, but this means that in the body-centered cubic, 68% of the volume of the cell is occupied by atoms.